In our last several videos, we've been working to build a strong foundation in our understanding of quadratic expressions. And while the skills that we've learned are important in their own right, the main reason we've been working on these skills is to give us tools for solving quadratic equations and graphing quadratic functions. As we discuss these new topics, though, our strategies will vary depending on which form of a quadratic we're working with. So let's begin making our way through these topics by learning how to solve quadratic equations using the factored form. To start things off, let's check out this equation. Notice that the expression on the left side of the equation is a quadratic in the factored form, and we want that expression to be equal to 12. As we've observed before, this factored expression is just the product of two sub-expressions, and so it might be helpful to think of a pair of numbers that multiplies to 12. For example, if we could get this first factor to be equal to 2 and the second factor to be equal to 6, then we would end up with 2 times 6, which is 12. So how can we make that happen? Well, we just have to replace the first x with a 3 and the second x with a 2, and we'll end up making the equation true. And if that's all it takes to solve quadratic equations involving the factored form, then this shouldn't be too difficult. Unfortunately, there's an issue with the solution that we came up with. We picked a different value for each occurrence of x, but what we actually want is a single value that we can plug in for both x's. That makes this problem significantly more challenging, and we can see why if we try plugging in a few different values for x. Let's make a table that represents the value of the quadratic expression on the left side of the equal sign. Then, let's plug in 2 and 3, which end up evaluating to 6 and 14 respectively. This might give us an indication that the actual answer is somewhere between 2 and 3, and if we tried out some decimal values, we could get increasingly close to 12. Still, it would be nearly impossible to get the exact answer just through guessing and checking. To illustrate another challenge here, suppose we modify our equation so that the factored expression needs to be equal to 6. Initially, this would appear to make things much easier since the factored expression evaluates to 6 when x is equal to 2. So our answer should be 2, right? Well, yes, x can be equal to 2, and that is a valid solution to the equation. However, there's another solution to the equation that we haven't encountered yet. If x is equal to -5, then the factored expression is once again equal to 6, which means that -5 is also a solution to this equation. It turns out that quadratic equations aren't limited to just one solution. Similar to absolute value equations, they can have up to 2 solutions, but there are also times when they'll only have 1 or even 0 solutions in the real numbers. This means that when we have a factored quadratic expression that's equal to a constant, there are a lot of unknowns that we need to take into account. So, why do we even bother trying to solve quadratic equations involving the factored form? Why don't we just convert the factored form into a different form that makes finding a solution easier? Well, there's a special situation where the factored form works out really nicely. Suppose we modify our equation again so that the factored expression is equal to 0. Initially, it might seem like we'll be stuck guessing at our solutions like before, but something special happens here. Since the factored form represents a product, we can think of this situation like this. Here, a represents the first factor, and b represents the second factor, and we want a times b to be 0. Now, one situation that will work here is if a and b are both 0, since 0 times 0 is definitely 0. But there are lots of other situations where two numbers multiply to 0. 0 times 4, -8 times 0, 1,439 times 0, 0 times 5.287. Basically, as long as one of the numbers in our product is 0, then the whole product will also be 0. And we can represent this by saying that a is 0 or b is 0. This conclusion is known as the zero product property, and will form the foundation of how we solve quadratic equations using the factored form. From here, we can go back to analyzing our actual equation. If we want our quadratic expression to be equal to 0, then either a or b needs to be 0. And since a stood for our first factor, which was x minus 1, we know that if x minus 1 is 0, then the whole quadratic expression will be equal to 0. The same works for b, which stood for x plus 4. This is the power of the zero product property. We are able to take one challenging equation and split it into two simple equations. And by solving these simple equations, we can see that x can be equal to 1 or negative 4. Then, just to verify that our logic in this process was sound, let's plug these values into our table, where we'll eventually see that both values do in fact make the quadratic expression equal to 0. So our application of the zero product property was successful. Now that we've explored the reasoning behind the zero product property, let's apply that property in several examples where the factored form of a quadratic is equal to 0. Let's consider this problem and start by drawing boxes around the factors on the left side of the equation. Once we do that, we know that one of those boxes needs to be equal to 0. So either our first box equals 0 or our second box equals 0. That gives us two equations to solve, and once we replace our boxes with the expressions that they each represent, we can see that we just need to do some subtraction to isolate our variables and get our answers. Thus, p can be equal to negative 2 or negative 9. Our next problem will be very similar, but let's solve this equation without doing any boxing. The main question to ask yourself here is, what are the individual factors that could be equal to 0? Thankfully, the parentheses in this problem make that answer pretty clear. So the expression inside the first set of parentheses could be equal to 0, but it could also be the expression inside the second set of parentheses. Then, if we add 14 to both sides of the first equation and subtract 3 from both sides of the second equation, we can see that q is equal to either 14 or negative 3. Next, let's check out this problem. While the expression on the left side of the equation is still in the factored form, it does look a bit different from the other problems we've encountered so far. We can tell pretty quickly that v minus 5 is a factor and can thus be equal to 0. And some people would stop there and say that this problem only has one answer. However, the factored form of a quadratic is always composed of two linear factors. So, what's the other linear factor here? Well, it's just v. Our variable is allowed to be a factor all on its own. And when we set that factor equal to 0, we get an equation that we don't even need to solve. We can simply see that v can be equal to 0. And just to be sure about our answers here, let's check our work to verify that we did indeed find solutions to our equation. Then, let's solve one more factored equation in the traditional manner to give ourselves a bit more practice with that process. Now, at this point in time, you might be thinking that our problem-solving process is getting a bit repetitive. You may even already know the solutions to this equation based on patterns that you've observed in previous problems. If so, you'll know that in this equation, m could be either negative 6 or positive 7. Essentially, our solutions end up being the additive inverses of the constants from our factors. Since the first factor has a constant of 6, the corresponding solution is negative 6. And since the second factor has a constant of negative 7, the corresponding solution is positive 7. Once you've made this observation, you may be tempted to forget about the zero product property and the formal solution process. Why not just remember this quick trick and move along to bigger and better things? Well, the short answer is that our factors won't always be this simple. Eventually, you'll encounter problems where there are more than two factors, or where the factors are much more complex expressions. In those cases, knowing when and how to apply the zero product property will be an essential skill, and it's important to build up that skill when working with simpler cases so that the more complex cases aren't as overwhelming. In fact, we can even get more complex cases when dealing with quadratics. Take this problem. Once we introduce linear coefficients other than 1 in our factors, our trick doesn't work anymore. If we guess that the solutions are -5 and +7, we'll see when we check our work that neither of those answers is correct. Instead, we need to follow our process by setting each factor equal to 0. Once we do that, we can see that we have two-step equations to solve rather than one-step equations, which will give us solutions of -5/2 and +7/3. Just for good measure, we'll plug these solutions into our original equation, and eventually we'll see that these are both valid solutions. Finally, let's look at these two equations. In our first equation, we can set each factor equal to 0 as usual, and after solving those new equations, we'll see that both of our answers are fractions. Our second equation, however, looks a little different. First, the expression on the left side of this equation contains 3 separate factors, so technically, we should set each of those factors equal to 0. It might initially look like we're about to get 3 solutions here, but when we examine our first equation more carefully, we can see that it's impossible. 8 is not equal to 0, so we can ignore that case. The other aspect that makes this equation interesting is that our two linear factors are both the same. Thus, when we find the solution that corresponds with each factor, we can see that our solutions are also the same, meaning that this equation only has one solution. While solving quadratic equations using the factored form and the zero product property can be a useful skill, it can also feel a bit contrived. Sure, this strategy works great if we happen to have a factored expression that's equal to 0. But what if it's equal to literally any other number? How do we approach the equation then? Or, what if we have an equation with a quadratic expression that's not in the factored form? Is there still a way to implement this strategy? Thankfully, there is still a way to implement the strategies we've learned in this video, even if our equation isn't set up exactly how we want it. We just have to put in some extra work to rearrange the equation so that it ends up in a form where we can apply the zero product property. Take this equation for example. We can't currently apply the zero product property because neither side of our equation is 0. This is actually quite easy to fix though. We can add 7 to both sides, and it will still be true. This means that the expression on the left side of our new equation is now equal to 0. There's still a problem though. Now that we've added 7 to both sides, the left side of the equation is no longer in the factored form. But once again, we know how to solve this issue. We can just convert this expression into the factored form. Sure, this will take a little time since we need to start by converting it to the standard form, but once we do that, we can apply the factoring strategies that we've learned previously and see that our original equation can be transformed into this new equation. At this point, we're finally allowed to apply the zero product property, which will show us that t can be equal to -4 or +2. And plugging these values into our original equation will verify that these are indeed the correct solutions. In general, no matter what kind of quadratic equation we're given, we can solve using the factored form by following 4 main steps. The first step is to get one side of the equation equal to 0. The second step is to factor the quadratic expression on the non-zero side of the equation. The third step is to apply the zero product property. And the final step is to solve the new equations. For our next example, let's look at an equation that has variables on both sides. While this is going to be more complicated than previous problems, remember that when we manipulate equations, we can add or subtract expressions that contain variables. Doing so results in this new equation, which satisfies our goal of getting one side equal to 0. But notice that we'll then have to factor an expression with a negative leading coefficient. Because negative leading coefficients can be kind of annoying, let's actually go back and approach this problem a bit differently. If we add 3b squared to both sides, then the quadratic term simply moves from the right side of the equal sign to the left side. But notice that the coefficient of the quadratic term also changed from -3 to +3. While this won't change the answers we get, this will make factoring a bit more convenient, so let's follow this path. From there, however, we still have to go through the challenges of factoring an expression with a leading coefficient that isn't 1. When we eventually get this factored form, though, we can finish the problem off by setting each factor equal to 0 and seeing that b can be equal to 5/3 or -2. Now, if that's all it takes to solve quadratic equations, then we should be set. While the examples in our last section may have felt a bit contrived, the examples in this section were much more authentic and gave us a better idea of how to solve any quadratic equation through factoring, right? Well, unfortunately, that's not really the case. Although the numbers in the last few examples may have looked more arbitrary, they were still specifically chosen so that the factoring process would work out nicely. If we truly choose more arbitrary numbers for a factoring problem like this, the chances are pretty high that we would get a quadratic expression that just isn't nicely factorable. Because of this, we'll need additional strategies for solving quadratic equations that can be applied more consistently, and we'll learn some of those strategies in our upcoming videos. But for the problems where the numbers do work out nicely, factoring is a great strategy to add to our toolkit in our approach to solving quadratic equations. That concludes this video on solving quadratic equations using the factored form. Hope you learned something new, and thanks for watching.